Okay, let's do a little math. Independent assortment leads to extensive genetic diversity. How much diversity? A lot of diversity. Let's take humans. You have 23 chromosomes. Yes, you have 23 chromosomes. So basically, there's an excess of about 8 million different types of possible gametes through independent assortment. So each offspring you have represents only one of 8 times 10 to the 6th squared, or 64 times 10 to the 12th potential genetic combinations. That's why you don't look identical to your siblings and everyone looks genetically diverse. It's just plain math of independent assortment. Okay, back to the laws of probability and how they explain genetic events. So genetic ratio, 3/4 tall, 1/4 dwarf, expressed as a probability. So you have about a 3/4 chance of having a tall P baby and a 1/4 chance of having a short dwarf baby if you're a P. It predicts the outcome of fertilization events. The probabilities range from 0, the event will not occur, to 1, the event will occur. Got a little carried away there. The probability of 2 or more independently events occurring simultaneously is equal to the product of their individual probabilities. Okay, so again, coin toss, 50-50 every time. Heads, tails, heads, tails. You do it twice, you have a 1/4 of a chance. This is exactly what we're doing when it comes to crosses. The sum law calculates the probability that possible outcomes of 2 events are independent of one another, but can be accomplished in more than one way. So that is how we use the sum law to determine that 9-3 to 3-1 ratio. Now, let's talk a little bit about chi-squared. Mendel's ratios are hypothetical. These monohybrid and dihybrid crosses are hypothetical predictions. If you had 4 babies, you probably wouldn't have one that's big D, 2 that's big D, little d, and 1 that's little d, little d. This is a probability. So based on the following assumptions, each allele is dominant or recessive, segregation is unimpeded, independent assortment occurs, and fertilization is random. Now, fertilization really isn't always random, but it can be. Influenced by chance events, subjects to random fluctuation. So one of the things we want to do, a chi-square analysis evaluates the influence of chance on genetic data. The outcome of independent assortment and fertilization are subject to random fluctuations from their predicted occurrences as a result of chance deviation. So what is it of chance? How are we going to determine how much of this is just chance and how much of this is actually genetically determined? 2 major factors for predicting genetic outcomes. Outcomes of independent assortment and fertilization are subject to random fluctuations as a result of chance deviation. So as sample size increases, the average deviation from expected results decreases. So as sample size increases, so you've got 1,000 seeds, the average deviation decreases. So all of a sudden your average is going to be closer together. The average deviation from expected results decreases. So you've got 1,000 babies, you're going to look more like it's predicted. You've had 2 babies, I don't know. Does that make sense? So the larger the sample size, the more likely that your prediction is true, the more likely that your data is correct, and it's not just a chance deviation. So the larger your sample size, the better your data. So your null hypothesis assumes data will give a certain fit, assumes no real difference between measured values and predicted values, and the difference is attributed purely to chance. So the null hypothesis would be rejected if observation deviation is not due to chance. So you want your null hypothesis to be rejected. You want to say, no, this was not just chance. I actually performed an experiment and I got the correct results. If you fail to reject your null hypothesis, it's saying that your observed deviations are just due to chance, just By random chance, this thing happened. By random chance, all of the P's were wrinkled or smooth. So a chi-square analysis is a goodness of fit test for your null hypothesis. It takes observed deviation and sample size into account. It rejects, not reject the null hypothesis. It's very confusing. You want your null hypothesis to be rejected. This is what you want. So let's look at some data. You've got your 3/4 versus 1/4 and your monohybrid cross. And in here, you've got of 1,000 babies, 750 versus 250. What you really got was 740 versus 260. That's pretty close. Your deviation is only plus or minus 10. So you're going to do the d squared divided by e. We will do this in class. Do not panic. And your chi-squared is going to be really good, actually, in this case. So basically, the odds are this did not just happen by chance. The same thing you can do with the dihybrid cross. What you observed, what you expected, and then you're going to subtract the deviation. You're going to square that number, and then you're going to take the deviation squared over your expected. And that's going to give you your number, and that's going to give you your chi-square. We'll do it in class. Don't panic. I'm just explaining to you what it is. The chi-square analysis requires degrees of freedom to be taken into account. Greater number of categories, more deviation as expected. N-1 is the number of different categories into which each data point may fall. Here's a graph for looking at some of the probability. We will do some of these in class, so I'm not going to, it's too small for you to see on the screen. Interpreting probability values, one of the number of degrees of freedom is determined, the x squared, the value is interpreted in terms of the corresponding probability. So if your p-value is a percentage of 26%, this indicates that if the same experiment was repeated 25, 30, 45, a bunch of times, 26% of trials expected to exhibit chance deviation. 75% show less deviation than initially observed as a result of chance. These p-values enable us to reject or fail to reject the null hypothesis. We want to reject the null hypothesis. P-values between 0.1 and 1 indicate observed deviation will be obtained by chance alone, 5% or more of the time. Conclusion: don't reject the null hypothesis. P-values of 0.5 or 5% indicates observation deviation obtained by chance alone, less than 5% of the time. Conclusion: reject the null hypothesis. This is good. We want to reject the null hypothesis. Okay.